Welcome everyone to a session about garbage collection and observing different types of garbage collectors. I'm happy to be here again at JFall as a speaker. It's a little bit unbelievable for me to be selected again, but I'm grateful to be here in front of you and looking forward to talking to you all about all this. I'm Anna. You can reach out to me on Twitter or Mastodon with your questions, but you can also reach out to me on LinkedIn. If you can remember my name from the program all the time, you can reach out to me there. But if you have questions, I prefer receiving the questions and not just generic connection requests, so that I would know that you would like something for me explained. I love explaining things, and maybe you would like to have that in written as well, that response. Maybe it would help you more. So please do connect with me after the session and ask me whatever you have in your mind and questions regarding Java in general, if possible, and maybe something related to Kubernetes, because I know a bit about that one as well, worked a bit with that one as well. And I still enjoy working with that as well. So I'm a developer advocate at Oracle, and I enjoy programming both with Java and Kubernetes. Today's session is going to be more on Java, as we talk more about garbage collection, which is Java garbage collection. But it's going to be a little part about containers as well. So the agenda of today has a few points. We're going to go through a bit of a theory. We're going to go and see why does choosing a garbage collector matter. The setup that I use to test my assumptions about garbage collectors and what I read about garbage collector and what I know about garbage collector. It'll be detailed to you. And of course, we're going to discuss the ergonomics through the applications that I used. By the way, the code will be shared, so you can try that at home. You can contradict me afterwards and say, no, I don't believe that that's the case. I love to be contradicted. And I have tried this setup a lot of times in order to get something as accurate as possible, but I always love to know more, especially that because this setup runs with Java 21, and maybe with other versions of Java would be different results, of course. So, those being said, I hope that we all love Java. We all love Java, but we all love garbage collection in Java because it automatically frees memory when that is happening. So for me, that was one of the selling points when learning Java, because I don't have to manage the memory whenever I am writing a Java a program in general. Probably many of you have started with other languages where you have to also manage the memory. And yeah, that's not that fun when you also have to think of solving a problem. So with garbage collection, well, that's the definition from Wikipedia, but what we know about it is that it tracks every object in the JVM heap and removes the unused objects. And that's awesome, right? Now, it performs 4 operations, and it allocates objects on the managed heap efficiently. That's most importantly, so it just doesn't allocate objects. It does that efficiently. It reclaims no longer used objects, it clears their memory, and keeps the memory available for future allocations. So these are 4 important operations. However, garbage collection primarily focuses and occurs with the reclamation of short-lived objects. Newer objects have shorter lifetimes, and older objects have longer lifetimes, obviously. Now, newer objects tend to be related to each other and accessed by the application around the same time. So, those being said, probably you heard about generational garbage collection. Did you hear about that term? Can you raise your hand? Good. And probably you know that it's called like this because it's based on weak generational hypothesis, which states that young objects tend to die young, while objects tend to stick around for a longer time. And probably you know that with the newer JDK versions, most of the garbage collectors are generational and not concurrent. Now, with the generational garbage collection, data is partitioned in multiple allocation regions or generations, which are kept separately based on the object age. And as the name it says, the young space, the young region, well, it keeps the newly allocated objects, while it has the newly created objects, the new objects that live beyond one GC cycle, and of course the objects that survive a few garbage collection cycles and move between the survivor spaces. Now, the old region, if an object has enough age, has reached a certain maturity, by surviving garbage collection cycles, well, it will be copied to the old region. And, well, as we covered probably earlier, the garbage collection rarely scans that region for collecting and seeing if there are no longer regional or reachable objects. And of course, there's a permanent metaspace region with objects stored there, like JVM metadata, core system classes, and other data that typically exists for near the entire duration of your JVM life. Without further ado, how does garbage collection, the generational one, works? Well, obviously, when an object or multiple objects are being allocated, they first go to the Eden space. Now, once the garbage collection cycle occurs, they are becoming of age of 1, so they get to a survivor space. Next, when the second garbage collection happens, this happens also with the newly allocated objects. They're again in Eden, then they go to survivor. But as I said earlier, the objects can be walked between the two survivor spaces, between the two survivor spaces, until they reach certain age to be called as old and be promoted there. So like the end cycle, sometimes like age 15 of a generational cycle, they get promoted to the old region, and they will be longer time for our application. Now, why does choosing a garbage collector matter? It matters because, well, we have to look at our context of our application. That's what we're going to do in the next 30 minutes. Because, well, the collectors strive to be as optimal as possible from every aspect, right? But they are designed to make different trade-offs and to support different use cases, like your applications. So sometimes when you look at your garbage collection, you have to analyze, like, do I really get the performance that I want with the current setup that I have for garbage collection? Can I afford to, are the GC policies enough and supporting what my application is trying to do? Or can I, maybe change that and have more performance from my application? And speaking of performance, we need to define that a little bit and how we're going to assess that. So we usually look at our application from 3 points of view. We look at the amount of successful operations that we can do with our applications. We also look at how much time that those took. We all strive to have like as much throughput as possible with little latency, and of course, with the memory footprint as small as possible. However, as I said earlier, achieving all 3 is a great goal, but sometimes we need just to focus on maybe 1, 2, or have like 3 at the medium value. And another way to look at our applications is by how our applications are. So applications have different aspects that we're looking on, and they consume memory, CPU, for example, and resources in that way, based on the operations that they're doing. So probably different garbage collectors will serve them to be at their best. So there are some CPU-intensive examples, like CPU-intensive problems usually are the type of problems that require a lot of processing power to solve. And you have in the slide some examples where you can identify what that means. It means usually like compressing or decompressing files, a lot of complicated actions when it comes to security, which is very important, but you should know that also requires a lot of CPU. Then rendering graphics, working with videos, that's also consuming CPU. And of course, mathematical operations. So if your application has complicated algorithms and performs a lot of math, then probably it will use a lot of CPU. Now, I/O-bound examples, on the other hand, means that a given task often waits for I/O. So, for example, networking, file I/O, so on, are usually slow compared to the CPU ones, but they are the kind of tasks that mostly focus on usage of memory. So, keeping that in mind, in these kind of 2 applications, let's look at the setup overview and see which garbage collectors are better for those. Now, in my setup, I really thought like, okay, I want to work locally, but I also want to work in the cloud. So in order to achieve that, I have created 2 simple Java applications. One of them is called Eager Factorial, which performs mathematical operations, like big factorials and lots of computation. So it's CPU intensive. It pushes my CPU to do like a lot of calculations whenever I'm giving it like big numbers. The second one is called continuous editor. So what that does, it continuously edits a file grows in size. It's more intensive, like from the I/O bound perspective. If you're thinking to your typical web applications that are backed up by a database, usually those are, you're looking from the I/O bound perspective. So that's a part with it. But there are situations when the mathematical part of it might be more interesting to observe. I containerized those with 2 Docker files. And of course, I threw them on Kubernetes and run them in Kubernetes. Now on local, I thought, like, how do I test them? How do I can test locally, but also in the cloud? So locally, I can test thanks to K6, which you can run from the CLI and just run tests to your local. However, if you're testing on local, your local machine probably it's a laptop, so it doesn't have as many resources as a Kubernetes cluster. So in the end, I end up saying, like, okay, probably it's more reliable to have this running in Kubernetes too, and use the power there to run my K6 tests and see some results. Then I also wanted to observe my applications in Prometheus and get some information from there, some metrics. However, since my applications are not depending on any framework, I just added micrometer, simple micrometer, and created my own metrics for my application. That can be done, like the basic metrics of the JVM that can be enabled just with micrometer, and you can add whatever you need for your application. So if we want to look at the app for a while, let me go to the other screen. So this is my K6 setup. This is a test suite in K6. And if I'm going to the settings, and the tests, you can see my 2 tests. The one that's called factorial is the eager factorial, and the other one is continuous editor. Whenever I say run now on the suite, these 2 start in parallel to execute with the details that they have. And I can override as well the variable and secrets or schedule them when I want to run them to perceive their running, their execution. When it comes to application and running my tests, well, let's look at the code part. The part of the code is like continuous editor. It has a pretty simple composition with the test, the Docker file, and of course the Kubernetes setup for it. And just in my pom.xml, I just used the micrometer version, and I've used the simple client for having my metrics exported to Prometheus as well. That's it. So just micrometer and Prometheus was enough to export my metrics about my application. And the same setup is done for eager factorial. So pretty much this is setting up an HTTP server, doing the mathematical calculations in one case and editing a file in the other one, and then sending that metrics to Prometheus. Pretty simple. So I want to observe my application, right? So now that I'm getting some metrics, I want to observe probably the throughput and the latency of my application. And one way to do that is by using my custom metrics, because I had to make my own custom metrics to, see how much the duration of the request is. So I created that manually. And of course, I need to assess the latency as well. Now, in my case, the interval is going to be 2 minutes. I know it's small, but we're going to discuss the interval too. Next, I want to observe the CPU and the memory. So these are pretty much more standard measures. And I said they're different from localhost 9090 in the query because I just don't want to look at the Prometheus consumption as well. And secondly, I can look also at monitoring the JC because I can look at the garbage collection and how much time the garbage collection is taking. And I can also look the number of garbage collections that occurred for a certain instance. By the way, when you see generation there, usually, as I said earlier, you're focusing on the newly created object. So usually you're focusing on the young space and how that goes, because that's where the action happens mostly. The old space belongs to the objects that have longer tenure for your application. Now, if we evolve this a bit, because this is just our rates, and get something more interesting, you can also look at let's get some kind of throughput based on the garbage collection, second sum and seconds total. And also look at the max duration for an instance. So these are the queries that I have used to observe things for my application. Now, how do we test this? There are different ways to start testing, but when I want to apply load, and I said I want to use K6, I said, okay, let's start with average load testing, not go with stress testing first and see what's going on. Let's go with average load testing. And you have in the slide here an example of average load test. Now, this one is set to 2 minutes. Now, in real life, average load testing, it kind of takes hours because you want to see how your application performs during certain hours. However, I just wanted results and I just let it for 2 minutes and see what's going on. How do you do the average load testing in real life? Well, you have probably some analytic tools that can give you information from your production environment about how many users do you get in average, right? If it's a new application, you probably get that estimation from your business, and they tell you, we expect of like this many people to use our application. Firstly, you have to set up a ramp-up period, like the time where the system needs to warm up to handle the traffic, and it usually should be like 5%, between 5% and 15% of the total test duration. And this one can let you compare the response times between different amount of users and the amount of requests that your application received at a certain point in time. Like see how it behaves at low load and see how it behaves at average load. Then average means keeping at a certain point and keeping a certain amount of requests keep coming or a certain amount of users using your application. And of course, ramp down period to like cool down your application and see how your application behaves when there's not much pressure on it after it was average stressed for a while. So that's pretty much the setup. And let's start with defaults, because defaults are great. We know it. We don't have to modify much when we're kind of starting to look at the performance. And maybe it's working great by default and we don't have to change anything, right? That would be the ideal case. And if we're looking at defaults and we're going to the JVM ergonomics page, we find out a few interesting informations. So first of all, the JVM takes decisions that are dependent on the platform that you're running the JVM. So it depends a little bit about, well, what operating system you're using to take decisions on what garbage collector is better and which defaults apply in that case. Most of the time, the garbage first collector is being selected, and you have there the constraints for it. So if there are two and more processors, and the available memory is more than 1,792 megabytes, G1GC is going to be the default. If the serial GC is going to be the default if one core is available, or you have an available memory of less than 1,792 megabytes. There's an initial heap size and a maximum heap size available. So please keep this in mind because I'm going to follow with a little question later. Serial garbage collector. Let's talk about the first one, the one that is selected by default when there's one CPU and memory less than 1,792 megabytes. Now, serial garbage collection performs all garbage collection on a single thread. It kind of has higher pause times, but it has a low resource usage. So that's what makes it great. And usually this is being used for machines that have like small data sets. And well, if you really want to use it, you can enable it with -XX plus use serial GC flag. So you can really have that there. On the other hand, fine-tuning it means to work with a few flags of it. So if you really want to like improve the performance of serial GC and see how it behaves in different situations, you can modify the max GC pause millis to provide a hint to the garbage collector that pause times should be less than the provided amount. That's because no default value is set for this flag, like you should choose this one, for example. Then look at the GC time ratio, like the time that is spent between performing GC work and application work. And of course, if you want to use string deduplication, because starting with JDK 18, string deduplication is available and can reduce memory footprint by about 10%. But it can impact the pause times of the garbage collector when this flag is being put there, so be careful on that. As I said, there's no like perfect situation. So, without being without further ado, I'm going to give you like 30 seconds to think about which garbage collector is being selected in this case, and somebody to shout it at me. What do you think? Sir. Okay, so we have here, say.
Just a second, I need to check something.
Don't ask ChatGPT, come on.
Because you mentioned if we have two processors, we need to G1, garbage first, right? And we have the two CPUs right now. So the first option is the best one.
Yes. So G1 GC is going to be the default selected one. Because the JVMC is like, okay, I have two CPUs available. I have two processors there. So I'm going to select that. And of course, the memory available is higher than 1,792. So in that case, for definitely serial GC is not a good option for my applications. So I didn't want to stress my applications with, putting them through some ordeal and, select this garbage collector knowing that the JVM kind of doesn't want it. So I went with the defaults, which was garbage first collector. Now, the garbage first collector has many advantages and is pretty much great for many applications by default because the garbage one collector divides the heap into smaller regions and it works with smaller memory segments to mark and sweep them. Now, it's the garbage collector that keeps track of the regions with the most unreachable objects those are being garbage collected first because it wants to free up the most memory from that. And what I wanted to say is that garbage one collector reclaims space mostly by using evacuation. So live objects found with selected memory areas are collected and copied into new memory areas, compacting them during the process. Why it was so great by default? Well, it works so great by default because it tries to meet the set pause time targets with the highest probability over a longer time. But it always waits for a certain given pause time, so you can find the details of why the defaults are so great. But if you're looking on the longer term, you might see that G1 can have a higher overhead than the other collectors, then that can affect throughput because of its nature. However, when you're starting your Java development, G1 GC being selected first, you're going to say okay, this is good for now. With certain maturity in your application, probably you're going to say that maybe it can be better. So I tested this with the examples that I used earlier, that I showed you earlier in the tests, but I reiterated them in the slides so that you would know. If you're wanting to enable it, that's the flag for it. And by default, the max GC pause millis is set to 200 milliseconds. So that's like a default value, unlike the serial one that doesn't have a default value. These were the test conditions. And well, I got some results. Now I'm going to look throughout time to results. Let me make this a little bigger. Hoping. We're going to look throughout time at two lines. The one that on the request duration, and of course the amount of requests that succeeded. So in this case, it's 7,704. We're going to look at average duration of a request, and we're going to look at the percentile 95, 99, and 99.99. Now, percentile 95 means that 95% of my requests are less or equal with the value that you see there. Percentile 99, well, just replace 95 with 99 and 99.99 the other one. So just to compare which ones will be better. Now, this is the first trial, and this is just the first batch of results. So these are going to be where is our starting point with our values. But these are the results for the application that is having intensive mathematical calculations, the one that is CPU bound. Now, if we're to look to the one that is I/O bound, there are similar results. We're not going to compare, by the way, the two applications. We're going to compare these applications in the different states. So this one, the count is kind of similar to 7,700 something in terms of requests, percentile 95, 99, and so on. I'm going to put these in a table at the end so that we can compare it better. Now we have need a benchmark for the CPU usage. So we look in Prometheus, and as expected, the application that is consuming a lot of CPU, the moment that it calculates more and more higher values for the factorial, it uses more CPU. The other one that is not doing much in terms of CPU usage is having a constant value for that consumption. And looking at the average over time of memory used, as expected, the one that is I/O bound uses more memory. The other one is kind of similar in memory usage for that. But I want it to be better, right? So I want to have, if possible, have better latency, lower latency, have better throughput, more throughput there, and of course, why not memory footprint lower? So I felt why not play a little bit and see what's going on there. So first of all, I wanted to see how can I fine-tune G1GC for latency. And for latency, I realized that I have to work a bit with the max GC pause millis, set it to a certain value, but also it would be good for me if I am setting the max heap size and the min heap size as well. So that's one, if I want to improve my latency. But if I want to improve my throughput, I can do that if I increase the maximum pause time, and this will make the generation sizing heuristics to automatically adapt to the size of the young generation, and this will influence, is this influenced by the frequency pauses, which is given by this value. Now, there are some other options to improve for throughput. In some cases, use the flag -XX, use large pages, but that depends a little bit about your operating system, so you have to enable that at the operating system level first to take advantage of that. Now, in case of my two apps, I decided for the first one to lower the pause millis, but set the memory values for it. So if I'm looking at it, I improve my throughput, but I can see that I had more impact on my latency as it is now lower and hopefully visible. On the other hand, let's have it here. Let's look at the results. So the average duration improved significantly in case of the one that is computing mathematical factorials. Personnel 95 definitely improved a lot, and you can see the difference in values. Personnel 99 and 99.9, there is definitely an improvement, half of the value that we had before. So we improved latency, but we didn't, from my point of view, we see a little improve in throughput, but we don't see a magical high number in throughput, which I'm happy for my CPU application. Latency is good, so, and also a good increase in the throughput. Now, after I observed some defaults, for my second application, I decided to change things differently. So what I did, for my second one, I said, look, I want to look into the throughput part of it. So for the second one, for the continuous editor, I want to improve the throughput. I will increase the pause millis because that's what I read in the documentation. It's good to increase the pause millis, but I also want to set the memory that's being used. So setting these definitely got me to an increased throughput, but also I got a great performance in terms of latency as well. So I could say that maybe it was a lucky coincidence that this happened, but I was pretty much happy with the results overall. Just improving the max GC pause millis and not adding the memory constraints, it had impact only on latency. I didn't see much improvement on the throughput side. That's what I see regarding the app. Now, increase of CPU usage was not much seen there. However, memory usage decreased for both applications after setting the memory limits. So some intermediary remarks was that I could adjust these details and have more requests served by the eager factorial at a lower latency, while I kept pretty much the similar amount of CPU consumption. So I'm pretty happy with what I got for my CPU-intensive app. And of course, similarly, I managed to decrease the continuous editor consumption in terms of memory, but I couldn't say that, I see much improvement there. So, parallel collector. I want to move next, so say okay, This was okay for me, but maybe I can do it better with a different collector if I just force my application to use it. Now, the parallel collector is also called the throughput collector. So this one should give me the best throughput from all of them. And this collector is trying to meet the goals. It's trying to meet some goals in a certain order. It tries to meet the maximum pass time goal first, then look at the throughput, and then look at the footprint goal. So it has like 3 goals that it looks all the time to adjust them. Why it works so great by default is because of this way of working and a way of like adapting the goals of it. So in this case, you have the formulas for the throughput and their impact on that. So when you set those values, you do have an impact on throughput. And then we also can impact more of the throughput by setting the flags for how the growing of young generation, old generation, and the percentage that the generation strings as well. However, for my tests, again, I started with the defaults and see what's going on happen. Now, on the defaults part, I could observe that compared to the other operation, I have a slightly increased value for my throughput. And that was the case for both applications, just with the default, with the use parallel GC. But I want to see, in terms of CPU usage and memory, was pretty much similar results like the defaults that I got the first time with the G1 GC. So I was like, maybe G1 GC was the lucky winner, you know? So I had some intermediate results. I could see that there were some intermediate results that made me happy, but not as I expected it. So I went into tuning this, as I used the formulas from earlier. So I thought like, okay, so how about to choose reasonable pause timing for my applications and adjust the throughput thanks to the GC time ratio. So in the first case, I adapted only the max GC pause time millis and set a value to it for 200. And in the second phase, I looked over, and the results on this next page. So I looked at the results of that, what I got. Well, just setting the pause time millis, my latency went very, very nice to low, and I got better throughput compared to the other sides. So I was like, okay, so just want this, and I had like great impact on my application. But this is the application that does mathematical operations. So just bear in mind that the mathematical operations with parallel GC perform great compared from all of the results here. Let's look at the continuous editor one. Now, continuous editor, on the other hand, I said, okay, I'm going to go for throughput for this one. So I'm going to set also the GC time ratio to 99 according to the formula. So I expect to see throughput increase, and I did. If I'm looking to the details with for the latency, well, latency improved a bit compared to the other one, but what I see mostly increasing is the throughput. So I was pretty much happy with the details that I set there. Looking at the continuous editor, the IO bound one, now I can see that I reached my throughput goal. I'm doing great in terms of latency, but looking at the overall chart, seems like G1 GC and parallel GC with improvements can get me to the same goal. So probably selecting one of them as my collector would be good. Now, increase of CPU usage, I didn't observe much change. And average over time of memory used, well, the memory use decreased significantly with this one. So from this point of view, I pretty much prefer parallel GC, especially for the eager factorial application. So the remarks here, because the memory and usage and latency are lowered, so far it seems to be winner for both. But all the time I have adjusted a few things there for my application to look over it. So let's go to the last one and see how that one performed. Now, the last one that I preferred was generational Z garbage collector. And just as a short intro for this one, the ZGC garbage collector was introduced as an experimental feature in JDK 11 and then was declared production ready in JDK 15. So this garbage collector exists already. But at its core, this was a concurrent garbage collector, and we talk about generational garbage collectors, right? So this is why we're using generational ZGC. So what this means that we can now, with JDK21, we can enable generational CGC thanks to two flags, with use CGC and -XX plus Z generational. Why I personally love to try this one is because I didn't have to set a lot of things for tuning it. So it kind of selects some flags by default. I don't need to go and set them for tuning it. All the time that I need to give for this garbage collector to work to a certain performance is a certain amount of memory, like to give the XMX flag there. So just the max heap size is needed for it. However, this garbage collector works best with big heap sizes, like when your application is using like a big heap size and not smaller one. So again, let's go for the test conditions for this one. Set the flags. Now, if just using the defaults for the eager factorial, I could see similar results as G1, GC and parallel. So I was like, not that much impressive for the one that is performing mathematical results. Maybe parallel could give me like better operations for it, better results for it. On the other one, that is IO bound, that is consuming memory, I could see increase of throughput and some value of latency that can be interesting to observe. So maybe ZGC would work better for the one that's IO bound. In terms of CPU usage, well, it's pretty much similar. I didn't change much there. While in terms of memory used, I saw an increase of memory usage for both applications. So I decided to tune things and use the flags that I set earlier for setting the memory for ZGC as well, because that's what the documentation said. All the time set -XMX, and it should be fine. Those flags and the XMX should be fine. So I compared again my tests. And looking at it, I could see that I observed that, well, my throughput has increased a lot for the eager factorial. However, if I'm looking to the results that I got for the latency, they are comparable with parallel GC, but they're slightly worse. So the one that performs mathematical operation, that's CPU bound, with ZGC, even fine-tuning it, didn't give me like something wow to be like, yeah, this is the one for it. On the other hand, for the other one, I could see a decrease in latency, significant decrease in latency. I could see a boost in throughput. So it did give me better results for the IO bound one. Now, if I'm looking at the increase of CPU usage, similar results, probably slightly increased for the eager factorial one. And I could see that, well, the memory is kind of contained in this case for both of them over time when setting it. So now let's look at the results. For the eager factorial results, I got the best for the one that's like performing mathematical operations and probably the best performance for it. I got it with parallel and of course fine-tuned parallel GC. So the best throughput and looking at the latency value, parallel worked best. It's as the name says, it's the throughput collector, gave me great values. Now, looking at the other one that's IO bound, here I had some mixed results. So I had like application request average duration, like better for ZGC, throughput better for ZGC. However, P99 and P99.9 were better in case of parallel. So I thought, and of course, P95 was comparable, like 4 milliseconds in difference. So I thought like, okay, maybe I can do something to compare both and see which one is better. So I went next to stressing the applications, because average is okay, but let's see how they do when the same application continuous editor is being stressed. Now, stress testing, it will give you worse results than in average load testing when it comes to latency and throughput, because there are more users that put pressure on your application. And, well, of course, the experience is going to be different. So the way that I did it, I put more load, I reused the average load script, and, well, expected the worst. So I increased the target of my users to 100 from 80, and changed the duration of my test, like the ramp up is 20 seconds. The duration of the amount of users that are going to stress my application is going to be 100, trying to send as many requests during 90 seconds. And the ramp down is only 10 seconds, so it's going to be even more abrupt. Looking at the results, well, the continuous editor, after changing the results here, and looking at what was with parallel, with stress testing, of course, the results are worse in terms of average and throughput compared to the initial ones when it was average. And, well, in terms of ZGC, the throughput consistently, give me a great throughput, while of course the latency is worse than initial that I had in my average. However, is almost at half compared to parallel. So for the continuous editor on the long term, ZGC gives me better results, while for the other one, parallel GC was the lucky winner. That was pretty much my talk. This is where you find the code that I use here, and you can challenge what I said earlier. And I'm looking forward to your questions as well. Thank you. Just raise your hands if you have questions and shout. Yes?
About CPU detections.
Yes?
Nowadays, the CPU is more like cores, power cores, energy cores. What's the CPU to Java?
So by the way, the CPU metrics that you see there, it's both user and the application itself. So it's not just the application consumption over there, the process CPU metric that I get there. And CPU to Java, I don't understand the question.
Like 10 years ago, you had a physical CPU with a core with one thread. Now you have 26 cores, 45 threads, power efficiency cores.
I don't know the formula, sorry. Sorry.
In clouds you don't even have cores
No,
anymore.
Yeah, I was going to say that.
Time slices.
Yeah. And Java just uses every 1000 milli
Yeah.
is one CPU, even though it isn't.
No. So it's very,
So that's how the JK.
Sorry. Yeah?
In your performance results, do you also take into account the higher or lower CPU utilization or memory utilization? So where you have all the tables, you see, okay, the latency is better or
So I always look at the peak, what's consumed most, the max of it. That's what interests me more. I know that it's not the same value all over the time, but I look at the max of it.
I presume if you have double the CPU usage, then okay, it's fair to have double the CPU throughput.
Yeah, true.
Is it worth determining the ratio of the throughput versus the amount of CPU used? Basically, that would be efficiency. How efficient am I utilizing my CPU to serve customer traffic versus am I just spending more cycles on GC?
That makes sense. However, I didn't want to alter that. I just used the defaults that was given to me by the container, so I couldn't, actually, I think I could do that, but I was not interested in altering those defaults all the time. There are a lot of moving parts in observing performance, improving all that, and
Yeah, so aside from setting the parameters on the JVM, we did a lot of tuning, but maybe now with the faster one, it is indeed faster, but it's also consuming 8 times more CPU power compared to the one that's only half of the speed.
I didn't see much change in the CPU and in the because on that one on ZGC, the memory is the one that is needed. The more memory your application is using, the better Gen ZGC is fit for that. For the other cases, parallel in most of the cases, parallel is the best.
Okay.
That's why it's the throughput collector. But in the cases where you have a lot of memory available, and there are some studies for Hazelcast, I think, where Gen ZGC performed very well. So in these cases, Gen ZGC does the best. But if you're having I don't know, just a typical application that doesn't do anything intensive with the database, then probably keeping parallel or maybe G1 would be enough. Would not be mandatory to go with ZGC. So I'm not recommending Gen ZGC all the time. This is the best for all the cases. It's just for the cases where you need to have the max heap size of a big value. That's where I saw it that gives the best results. In the other cases, I don't think it would be worth of going through that effort, because there's also the memory consumption that maybe, yeah, it would be better just to keep it to parallel.
Okay. What is big?
Big in my case was like 2,816 megabytes. I haven't tried it for lower than 1 gigabyte, to be fair. And I wouldn't go for lower than 1 gigabyte just for the sake of, using a certain garbage collector.
Yeah. Okay, thank you.
And can go up to terabytes of memory if you have available for your application. Yeah. Any other question? Yeah.
You configured the string deduplication, and I was in the assumption that it only worked on G1 GC, but it changed. But you didn't mention that it only works for other garbage collectors since JDK 18.
Yeah, I didn't mention that. I think I mentioned only one time for the serial. That's it. But that's true for the string deduplication. It works since JDK 18 for the others as well. You watched Billy's new sip of Java?
I googled.
Because so my colleague Billy Corando made made the road to 21, which covers the changes in terms of performance between Java 17 and 21, and that's where he mentioned the string deduplication change for the garbage collectors. Yeah, I know. Oh, forgot. This is also, so the slides will be shared with you. Okay, I'm going to share the slides, of course. So what I would recommend you to follow we also aggregate these blogs on inside.java, right? So if you want to see all the GC materials that we have aggregated about garbage collection, go to inside.java and look at the tag GC. So you find a lot of documentation there. A lot of research done there. Now, Per Liden focuses on ZGC. Thomas Schatzel focuses on the other ones, G1, parallel, serial. So they kind of publish from time to time what has changed in the garbage collector in a certain version, in certain JDK versions. However, if you're going to the blogs, you're not going to find all the Java versions since 8, for example, but the recent ones are covered. So yeah. Well, since I was going to share the slides anyway, I thought that, we're going to look at the links at the end. And of course, there are other folks that look into GC and do micro benchmarks with different garbage collectors and publish that on their blog. So that's why we aggregate them on inside.java by the tag GC. So that's pretty much important to be known. Any other questions? There's no. Yeah.
But not all of them. Doesn't it affect the other GCs? Because if you have a larger heap size, there are less GC runs probably needed.
Less cycles needed. That's. Yeah, so the purpose of the test were as follows. In the beginning, I just wanted to use the defaults. And on the second run on the improvements, that's when I set the max heap size. So that if you're looking through the examples, there's always defaults first and then improvements with the heap size second. That was always keeping them the same setup for all the GCs, always have start defaults and then change those details. So that nobody says oh, okay, but in one case it was default plus the max heap size, and the other one was another one. And I think the talk would have been even longer if I would have went through all the flags that could be changed. What I played a little bit with the -XX use large page sizes for the second application. However, I realized that I have to work a little bit with the operating system to get relevant results in terms of throughput. But most of the time, when you have an IO-bound application, if you're using the -XX use large page sizes, that one can give you better throughput. Of course, if you enable that at the operating system level as well, because initially I didn't do that when I was running my tests. And I didn't see much change. And I was like, oh, why do they say this in the documentation if it's not doing much? And then I saw that there's a connection with the operating system as well. And not all operating systems support that. Yes?
It even gives a warning if you configure it and it's not available.
Yeah. Yes. True. But I had to try it with the defaults. Come on. It's not like somebody said like tuning garbage collection is something empirical. And most of the time it is. There are tools that nowadays can help you to not make this, like a wild guess. But yeah, let's say that first time we started empirically. Thank you. Any other questions? Yeah, there.
I realize that choosing a different type of garbage collector should have a dramatic impact on performance, but you also have shown us that choosing a different tool style will sometimes have a really dramatic effect, like hopping from 80 milliseconds all the way down to 8.
Yeah. So sometimes, well, I chose let's say the flags that would give a dramatic impact, first of all, and it was a dramatic impact during several runs of the tests. So these tests were run in average, I think, like 40 times per each configuration. That's why I have like 200 and something runs for my factorial. So I wanted to have like consistent, to compare a little bit the results and not like have like once great results and then like disappointing results. So I selected something that from the results, when I saw that I have consistency, like difference in throughput, like let's say 8 requests more compared to the other one, it didn't mean much change for me. So I could select one of them. And I usually selected the worst result, especially from the tuned one, to see, to not create high expectations. If you're tuning, you're always going to get this. So the worst results are pretty much in my slides for the tuned part.
In your opinion, in your experience, is it worth it to fiddle with pulse types or not, or to focus just on choosing a specific type of garbage collector instead of
So usually you start with just a specific type and see if the default selected is working. And then the second value is the pause times. It's always like if you want to fine tune it, the max to the GC pause millis is the one that's recommended.
not have any impact, not have that much impact choosing a pulse type.
So defaults are great. Look, as you saw, it was not like it doubled in throughput. It were just a couple of hundreds more of requests. It was during the same time. If it would have doubled in throughput, that would have been some big impact, of course. And also the max GC pause time millis is like a value of reference. The pause time should be less than that, but doesn't mean it always have to be equal and reach that pause time. Thank you. Well, if you have any more questions, we can talk afterwards.